Have you ever gazed upon a star-filled night sky and wondered, where did it all begin? What is the origin of this magnificent cosmic tapestry that stretches beyond our imagination? The vastness of the universe, with its billions of galaxies and trillions of stars, is a sight that sparks curiosity in us all. Each star, each galaxy, is a chapter in the grand story of the cosmos. But perhaps even more intriguing is the question of how this incredible expanse came to be. How did the universe, in all its complexity and beauty, emerge from what seems like nothingness? How did something as vast and complex as our universe arise? What processes and events led to the formation of everything we see around us? The answer, many scientists believe, lies in an event of unimaginable power and scale: the Big Bang. This monumental explosion set the stage for the birth of the universe. This theory, supported by a wealth of evidence, suggests that our universe began from a state of extreme density and temperature, a singularity where all matter and energy were concentrated, expanding and evolving over billions of years into the cosmos we observe today. From the initial explosion, the universe has been continuously expanding, cooling, and forming structures like galaxies, stars, and planets. The remnants of this explosive beginning can still be observed today in the form of the cosmic microwave background radiation, a faint glow that fills the universe and provides a snapshot of the early cosmos. Through the relentless efforts of astronomers and physicists, we continue to uncover the mysteries of our universe's origins, piecing together the story of how everything came to be from seemingly nothing. The Big Bang Theory is the prevailing cosmological model for the universe. It describes the universe from its earliest known periods through its subsequent large-scale evolution. Put simply, the Big Bang posits that the universe began from an extremely hot, small, and dense state and has been expanding and cooling ever since. This expansion wasn't an explosion of matter into a pre-existing space, but rather the expansion of space itself, carrying matter along with it. Think of it like dots on a balloon. As you inflate the balloon, the dots move farther apart, not because they're moving across the surface, but because the surface itself is expanding. At the very beginning of the Big Bang, according to the theory, all of the universe's matter and energy were concentrated into a single point of infinite density and temperature, known as a singularity. This point was not located in space as we know it. Rather, it was the entirety of space itself, compressed into an infinitely small volume. Imagine, if you will, the entire vastness of the universe, with all its stars, galaxies, and planets, squeezed into a space smaller than an atom. This is the unimaginable state of the singularity, a concept that stretches the limits of our understanding of physics. The Planck Era refers to the earliest period in the history of the universe, from 0 to approximately 10 to the power of -43 seconds after the Big Bang. This incredibly brief moment marks the boundary where our current understanding of physics begins to break down. The conditions were so extreme that our conventional theories like general relativity and quantum mechanics cannot fully describe what was happening. This period is named after Max Planck, the physicist who developed the Planck scale, which defines the fundamental limits of our current understanding of physics. Max Planck's work laid the foundation for quantum theory, which has since become a cornerstone of modern physics. His contributions have allowed scientists to explore the universe at its most fundamental level, pushing the boundaries of what we know. During the Planck era, the universe was so hot and dense that the four fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, are thought to have been unified into a single force. This unification is a key concept in the quest for a theory of everything, which aims to describe all physical phenomena in a single framework. Understanding this era could unlock answers to some of the most profound questions about the nature of reality. The physics governing this period is still not fully understood, and it remains an active area of research in theoretical physics. Scientists are developing new theories and conducting experiments to probe the mysteries of the Planck era. Advances in technology and experimental techniques such as particle accelerators and space telescopes are providing new insights. As we continue to explore this enigmatic period, we move closer to uncovering the fundamental truths of our universe. Section 5. Gravity's split, shaping the universe we know. As the universe expanded and cooled in the moments after the Big Bang, It crossed a critical threshold where gravity separated from the other fundamental forces. This separation marked a significant turning point in the universe's evolution. With gravity now acting as a distinct force, it began to influence the distribution of matter and energy in the universe. This separation paved the way for the formation of structures like stars, galaxies, and ultimately, planets. Section 6. Cosmic inflation. A universe expanding faster than light. Shortly after the Big Bang, the universe underwent a period of exponential expansion known as cosmic inflation. During this incredibly brief period, lasting for a tiny fraction of a second, the universe expanded by a factor of at least 10 to the power of 26. This exponential expansion is thought to have smoothed out the early universe, making it remarkably uniform in all directions. Cosmic inflation is a key concept in modern cosmology, explaining several observed features of the universe. Section 7. A universe of particles, from energy to matter. As the universe continued to expand and cool following inflation, the energy density decreased to a point where fundamental particles, like quarks and leptons, could condense out of the primordial energy bath. This marked the transition from a universe dominated by energy to one populated by matter. Imagine a sea of energy cooling and crystallizing into the building blocks of matter. This is the remarkable process by which the universe began to take on a more familiar form. Section 8. Building blocks of matter, protons and neutrons emerge. As the universe cooled further, quarks, the fundamental particles that make up protons and neutrons, combined to form these heavier particles. This process, known as baryogenesis, is still not fully understood but is crucial to the existence of the matter we see around us. Protons and neutrons are the building blocks of atomic nuclei, and their formation paved the way for the creation of atoms, the basic units of matter. Section 9. The first elements, hydrogen and helium, light up the cosmos. Around 3 minutes after the Big Bang, the universe had cooled enough for protons and neutrons to bind together and form the first atomic nuclei. This process, known as Big Bang nucleosynthesis, primarily produced the lightest elements, hydrogen and helium, along with trace amounts of lithium and beryllium. These first elements, forged in the fiery aftermath of the Big Bang, would later become the raw materials for the formation of stars and galaxies. Section 10. Echoes of the Big Bang, the cosmic microwave background. Approximately 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with atomic nuclei, forming neutral atoms. This process was crucial because it marked the transition from a hot, dense plasma to a more transparent universe. Before this event, the universe was opaque, with photons constantly scattering off free electrons. But as the universe expanded and cooled, these electrons were able to settle into stable orbits around nuclei, creating the first neutral atoms. This event, known as recombination, marked a significant turning point because it allowed light to travel freely through the universe for the first time. The universe, which had been a glowing fog, suddenly became transparent. This light, freed from the dense fog of the early universe, began its journey across the cosmos. It is this ancient light that we can still observe today. This first light, which has been traveling through the universe ever since, is now detectable as a faint glow of microwave radiation known as the cosmic microwave background, or CMB. The CMB is essentially the afterglow of the Big Bang, a relic from a time when the universe was just a few 100,000 years old. It fills the entire sky and provides a snapshot of the universe at that early stage. The CMB provides a snapshot of the universe as it was in its infancy, offering invaluable insights into its early conditions. By studying the CMB, scientists can learn about the composition, structure, and evolution of the universe. It reveals tiny fluctuations in temperature and density that eventually led to the formation of galaxies and large-scale structures. The CMB is a cornerstone of cosmology, helping us understand the origins and fate of the universe. Section 11. The universe's fate, an ever-expanding mystery. The Big Bang theory provides a compelling explanation for the origin and evolution of our universe, but it also raises profound questions about its ultimate fate. Will the universe continue to expand forever, growing colder and darker with time, or will gravity eventually halt the expansion and pull everything back together in a big crunch? The answers to these questions remain elusive, but ongoing observations and theoretical work continue to refine our understanding of the universe's destiny. One thing is certain, the universe is a place of wonder and mystery, and its story is far from over.